So before we get to the range rule of thumb, we want to mention about what values are usual or unusual for a data set. So usual values would be within 2 standard deviations of the mean, and unusual values are in general considered to be those which are more than 2 standard deviations from the mean. So just keep that in mind going forward. And in terms of a standard deviation, we can make a rough estimate for that, and I mean rough, by just taking the range and dividing by 4. So the range, of course, is the max minus the min. So max minus the min over 4 is a rough, standing on 1 foot sort of estimate for the standard deviation. For a more careful calculation, of course, you're going to use software. So the empirical rule is something that applies to bell-shaped data and would give us, if we have a data set that adheres to what's called the empirical rule, then we would have a pretty good idea that the data set is well approximated with a bell-shaped or normal curve. And so what the empirical rule is it gives us the percentage of data within 1, 2, and 3 standard deviations of the mean. So according to the empirical rule, within 1 standard deviation of the mean, we should find about 68% of the data. So that you can see that according to this picture, if we have bell-shaped data, it's symmetric about the mean, and if 68% of the data is within 1 standard deviation, that would mean about 34% of the data would be from the mean to 1 standard deviation beyond the mean in either direction. So that's the first part of the empirical rule. The second part is that 95% of the data should be within 2 standard deviations, and almost all of the data, like 99.7%, almost all of the data should be within 3 standard deviations. So in terms of using the empirical rule, there is an exercise on Canvas about using R to assess whether or not the cholesterol data seems bell-shaped. So you can assess whether or not it's bell-shaped by looking at a histogram, for example, but you could also see how well it adheres to the empirical rule by checking out the percentage of data within 1, 2, and 3 standard deviations of the mean. And again, there's a page on Canvas that goes through that, and then I also put the notepad file that has the R code on Canvas as well, so that you can go through those calculations. Now, z-scores. A z-score is the number of standard deviations a particular value is away from the mean. So this expression for a z-score, in this expression, x bar, you should know, is the sample mean. S, you should know, is the sample standard deviation, and x in this case is a particular data value that's of interest. So if we wanted to know the z-score of a particular data value, we would use this formula, and we would put the value of interest here, subtract from the value of interest the sample mean, and then divide that quantity by the sample standard deviation. So this would give the sample, the z-score for the data from that sample data set. If for some reason we had a population, then we would use go through the same procedure, only in that case, however, you can see on the right, mu represents the population mean and sigma represents the population standard deviation. So the z-score for a particular value, again, you're subtracting the mean and dividing by the standard deviation. So z-scores are used to compare the relative position of data values. A data value, how many standard deviations it is away from the mean in either direction, above the mean or below the mean. And also, a z-score could be used to assess whether or not a data value is unusual, an outlier. Why? Well, so think about that. We do have a rule of thumb that says, you don't have to think too hard because I'm about to say something. We do have a rule of thumb that says anything beyond a data value beyond 2 standard deviations of the mean is suspicious. We would want to look at that carefully and see, what's going on with those values. So they are potential outliers. Okay, so here we have an example where we're going to to apply the empirical rule. So if you take a moment and read this, read the statement of the problem. So here you see that the manufacturer of batteries claim the average length of life for a grade A battery is 60 months. However, the guarantee on the brand is 36 months. Okay, so that's interesting because there's a big difference there. Suppose the standard deviation of the life length is known to be 10 months and the frequency distribution is bell-shaped. So that's your key that, that the empirical rule will apply. Approximately 1% of the batteries will last more than 50 months, assuming the manufacturer's claim is true. So what's the manufacturer's claim? The manufacturer's claim is the mean is 60 months, and the standard deviation is 10 months, and it's bell-shaped data. So what percentage of batteries should last more than 50 months? So we would want to know the z-score for 50 months. So if X is the life of the battery, and we're given the mean is 60 months, the standard deviation is 10 months, and the data is bell-shaped, then the z-score for 50 months is -1. So that means it's less than, well, it's 1 standard deviation below the mean. So the percentage of scores that should be larger than -1 is, well, 0.5, 50% of the data is larger than the mean, because the mean is the midway in a bell-shaped data. The mean, the data is symmetric about the mean. So half the data is larger than the mean. So the percentage of scores larger than -1, well, half the data has a z-score of 0 because the mean has a z-score of 0. So that's the 0.5. And then the 0.34 is the percentage of scores, assuming, again, that it's bell-shaped, the percentage of scores between -1 standard deviation up to the mean. So that's 0.34. So 84% of the data should be larger than the values having a z-score of -1. So we would expect 84% of the data of the batteries to last more than 50 months. Okay, so in part B, approximately what percentage of the batteries will last less than 40 months, assuming the manufacturer's claim is true? So again, we would want to know what's the z-score, how many standard deviations is 40 months away from the mean, which is 60 months. So again, the z-score for 40 months is -2. So we want to know the percentage of, assuming bell-shaped data, what's the percentage of scores less than 2 standard deviations away from the mean. So we want z less than -0.2. So if you look at, let me find it. If you look at this bell-shaped curve, 0.035, here's a z-score of -2. That would be 2 standard deviations below the mean. And then the percentage of data less than that would be 0.0235. And then beyond 3 standard deviations from the mean is 0.015. So you would have to add those up to answer the question. So where are we? So 0.025, so that's 0.025 or 2.5%. About 2.5% of the data is less than 2 standard deviations away from the mean. So about 2.5% of the batteries will last less than 40 months. Okay, so now part C, suppose you get a battery and it lasts 37 months. What do you think about the manufacturer's claim? So in other words, your battery doesn't last very long. I mean, it's, according to the manufacturer's claim, it should last 60 months and yours only lasts 37 months. Right? So you're in that lower tail. Only 2.5% of the batteries should be in that lower tail, and you got one of them. So what do you think about that? Well, so either you got an unusually bad battery, and that was an unusual event, or what the manufacturer says is simply not true. So those are the possibilities there. We'll look at two more examples. So take a moment and read the first example. Okay, so here we see a bank employee believes her salary is low, and the information she collects is that the mean salaries is $64,000 and have a standard deviation of $2,000, and her salary is $57,000. So you can apply the empirical rule if the assumption is made that the salaries are bell-shaped. If the salaries are not bell-shaped, the empirical rule does not apply. So that would have to be true of the data in order to apply the empirical rule. So the question here is, does the information support her claim of discrimination? Well, if X here is employee salary, and the information that we know about employee salary is that the mean is $64,000 and the standard deviation is $2,000, and if we also knew that the distribution for the data is bell-shaped, the question we're asking is if the value of 57,000 is low, right? If that's low on the scale. So if you find the z-score of that, that's negative 3.5. That's a really unusual value. In a bell-shaped data, that would mean more than 3 standard deviations below the mean is her score. So that's unusually low. So if the assumptions here are true, then that's a very strong case that her salary is low compared to the other salaries. It's less than 1% chance that she should have a salary like that. So that is very, very unusually low. Okay, there's one more example here. It's the mean time to assemble a product. It took 22.5 minutes. The standard deviation is 2.5 minutes. What's the z-score for an item that took 20 minutes to assemble? So again, the mean is the value of X of interest. I said the wrong thing. Let me try that again. The z-score for an item that took 20 minutes to assemble is the value of interest, which in this case is 20 minutes, minus the mean, which is 22.5 minutes, divided by the standard deviation. So negative 1. So less than, she was less than the mean. So 1 standard deviation away from the mean, below the mean, was the assembly time. So it took less time to assemble, obviously, because you can see that, but it was 1 standard deviation below the mean is her z-score. What about for an item that took 27.5 minutes to assemble? Well, you can see right away that's above the mean. And how far above the mean is it? It's 2 standard deviations above the mean.